If I told you there might be a shortcut through the universe, one that could turn a 100,000-year journey into a step, you'd probably picture a glowing sci-fi tunnel. Now here's the pattern interrupt. Wormholes didn't come from science fiction. Science fiction borrowed them from real physics and then wildly oversold them. So what is a wormhole really? In the most honest, evidence-based way, a wormhole is a hypothetical connection between two separate regions of spacetime, predicted as a possibility by Einstein's theory of general relativity. Not a portal we've found. Not a tunnel NASA discovered. A mathematical doorway that the equations allow, under extremely strict, controversial conditions. To understand wormholes, you need one mental image. Spacetime isn't just space. It's a four-dimensional fabric, 3 dimensions of space plus time, whose geometry changes in the presence of mass and energy. In general relativity, gravity isn't a force pulling you. It's the shape of spacetime telling matter how to move. Planets orbit because spacetime is curved. Light bends because spacetime is curved. And if spacetime can curve, the next question is irresistible. Can it fold? Imagine a sheet of paper as space. 2 dots far apart on the sheet represent 2 distant places in the universe. Normally, you'd have to travel across the paper to get from one dot to the other. But if you bend the paper so the dots touch, you could poke a pencil through and connect them. That pencil tunnel is the popular wormhole idea, a shortcut through the geometry, not through normal distance. Now the controversy. The first wormhole-like solution that showed up in the math wasn't the travel-friendly tunnel you're imagining. In 1935, Albert Einstein and Nathan Rosen described what's now called an Einstein-Rosen bridge. It's related to the equations for a black hole, and it mathematically connects 2 regions of spacetime. Sounds promising, until you hit the catch. In the simplest form, that bridge is not traversable. It pinches off too fast. You don't cross it, you get trapped by horizons. In other words, the original wormhole is more like a beautiful equation than a usable route. Decades later, the wormhole conversation got its biggest serious upgrade. In 1988, physicists Michael Morris and Kip Thorne studied what it would take to make a wormhole traversable, meaning you could, in principle, pass through and come out somewhere else without being crushed, incinerated, or cut off from the rest of the universe. And this is where the story gets deliciously uncomfortable, because the price tag for a traversable wormhole isn't money or rocket fuel. It's exotic matter. Not exotic like rare element. Exotic like it behaves opposite to the normal rules. To hold a wormhole open, the equations require matter or energy that violates what physicists call energy conditions. Basically, the common sense expectation that energy density is positive. Normal matter has positive energy density. It attracts gravity. But to stop a wormhole from collapsing, you need something that creates a kind of gravitational push outward, like anti-collapse scaffolding. Here's the second pattern interrupt. Physics does allow negative energy, but only in very constrained, very subtle ways. In quantum field theory, empty space isn't truly empty. It has fluctuations. Under specific setups, you can produce regions where the energy density is effectively negative compared to the surrounding vacuum. The most famous example is the Casimir effect. Put 2 uncharged, parallel metal plates extremely close together in a vacuum, and quantum fluctuations produce a tiny attractive force between them. This effect has been measured experimentally, and it's real physics, not speculation. So does that mean wormholes are possible? This is where people argue. Yes, negative energy can exist in quantum theory, but there are strong limits on how much negative energy you can produce, how long you can maintain it, and how it must be paid back by positive energy elsewhere. Physicists call these constraints quantum inequalities. The short version is brutal. The kind of negative energy you can create in the lab is incredibly tiny and tightly regulated by nature. Keeping a macroscopic wormhole open would likely require negative energy densities far beyond anything we know how to generate, and maybe beyond what the universe allows. Now let's challenge a belief you might not even realize you have. Many people assume the main problem is building a wormhole. But even if one existed naturally, stability is a nightmare. Wormholes tend to collapse under small disturbances in many models. A stray bit of radiation, a particle drifting in, even the act of trying to send information through could destabilize it. So the cool tunnel idea is fighting not just engineering limitations, but the universe's own bookkeeping. And yet, there's a reason wormholes won't die as a scientific idea. Because they keep showing up again and again whenever physicists push spacetime and quantum mechanics to their limits. One of the most talked about ideas in modern theoretical physics is the connection between wormholes and quantum entanglement. In 2013, Juan Meldacena and Leonard Susskind proposed a conjecture often summarized as ER equals EPR, linking Einstein, Rosen bridges, ER, with Einstein, Podolsky, Rosen entanglement, EPR. The headline that went viral was basically, "Entanglement might be a wormhole." But careful, this does not mean you can entangle two particles and open a travel portal. The wormholes in this framework are typically non-traversable. They're more like a deep geometric way of describing correlations than a highway for spaceships. Then, in 2016, a result by Ping Gao, Daniel Jafferys, and Aaron Wall showed that in certain highly idealized conditions, often discussed in the context of anti-de Sitter ads, space, and holographic models, quantum effects can make a wormhole effectively traversable for information, not by smashing through with a rocket, but by carefully arranging interactions that mimic negative energy in a controlled way. And in 2022, a team including Jafferys and colleagues reported a quantum simulation, published in Nature, where a small quantum processor implemented a toy model consistent with traversable wormhole dynamics in a holographic setting. Pattern interrupt again. They did not create a real wormhole in spacetime. No portal opened in a lab. What happened was closer to running a faithful simulation of a wormhole-like process, showing that the math isn't just fantasy. It can correspond to real, testable quantum behavior in the right model. That's still a big deal, but it's not a Stargate. So where does that leave us observationally? What does the sky say? Right now, we have zero confirmed evidence of natural wormholes. What we do have are increasingly precise observations of black holes and strong gravity. And that matters because wormholes can sometimes mimic black holes from far away. Scientists have proposed ways wormholes might reveal themselves: unusual gravitational lensing patterns, distinctive shadows, or specific signatures in gravitational waves. The Event Horizon Telescope images of M87*, first released in 2019, and Sagittarius A** at the center of our galaxy, released in 2022, match what we expect from black holes remarkably well. That doesn't prove wormholes don't exist, but it does squeeze many alternative models. Meanwhile, gravitational wave detectors like LIGO, Virgo, and CAGRA test how compact objects merge and ring down. Some papers have suggested possible echoes that could hint at exotic alternatives to black holes, but those claims remain debated and not confirmed with high confidence. In other words, if wormholes are out there, they're either rare, well hidden, or not shaped the way the most optimistic theories want. So here's the honest, research-grounded answer to what is a wormhole. A wormhole is a mathematically allowed geometry of space-time and general relativity, potentially a bridge between distant regions, that becomes traversable only if you can arrange exotic energy conditions that we don't know how to produce at meaningful scales, and that nature may strongly restrict. It's a real idea in theoretical physics, a serious topic in quantum gravity discussions, and an open question in observational astronomy. And the most controversial part? Some physicists think wormholes are a clue to the deepest structure of reality, linking space-time to quantum information. Others think traversable wormholes are essentially forbidden once the full laws of quantum gravity are accounted for. The equations tease us. The universe hasn't confessed. If you enjoy explanations that separate what physics actually says from what the internet wishes it said, follow for more, because the next breakthroughs in gravity, quantum mechanics, and black holes will decide whether wormholes stay math or become measurable science. So what do you think? Are wormholes a real feature of nature we haven't detected yet, or a mathematical loophole the universe will never allow?